everybody. Welcome to this afternoon's tutorial session on Docker for data science. My name is Aly Sivji. I'm currently a grad student at Northwestern, where I'm studying medical informatics. And I'm also a software engineer at a startup called Dividos. It's a subscription-based retail pharmacy company, so think Blue Apron, but for pharmaceutical medications with a mobile application.
My name is Joe Jasinski, and I have a bachelor's and master's in computer science. I've been working with Python and Django for about 10 years, in which case I have had opportunities to work with Docker on many occasions. Now I'm currently at Nielsen, where I'm working on a large data science platform where I work with Docker and Kubernetes on a daily basis.
Hello, my name is Tathagata, but for making everybody's life easy, I go by T. I work in Chicago for a company called Here Technologies, and we are building maps for self-driving cars. Also, together, we organize the Chicago Python user group. So if you're in Chicago, say hello.
It's a lot of fun. All right, so today's agenda, we're just going to go over the rules of the road for this tutorial. I'll introduce the data science for some background and have some context for the rest of the presentation. Then we'll go over Docker with a couple of hands-on labs. Then I'll show you how to use Docker within some of your data science workflows. We'll have another hands-on lab for that, and then we'll lead into the break. Coming back, Joe is going to teach you about Docker Compose, and then T's going to walk you through an application we made that contains multiple containers. So stay tuned for that. So the way this is going to work is we're just going to have a little bit of a lecture section before we go on to the lab. We have a link to our GitHub repo, and that's where we have all of our instructions. There's also a link to the slides there. We're going to have dedicated question and answer sessions right after most labs, but raise your hands during the labs if you need help, and one of us will come by to help you out. And just if you're raising your hand and asking a question, just make sure it's something that's not really specific to your workflow. We're all going to be here all weekend. I'm going to be here till Thursday, so if you have any questions, feel free to reach out at a later time, and I'll be glad to help you out. So yeah, this is our repo, their instructions. I highly recommend getting started right now. If you're running a Windows PC, we have images we have VirtualBox images, so you can just load up a Linux distribution that contains all of our images with Docker and Docker Compose installed. So let's get started. So what is data science? Data science is about extracting value from data. It's about turning your data into actionable insights. And this can mean many different things. We can visually explore our data. We can build predictive models. We can classify observations into groups based on similar characteristics. Or we can build data-driven applications. So first and foremost, we have to remember that data science is a science. We have a question that we want to answer, a hypothesis of why something is happening. And our solution is not just our findings, it's also the steps we took to get to a result. And so what this really means is that reproducibility is really important, and our analysis, it needs to be repeatable. So reproducible workflows in data science make it easier to communicate results. We can use our methodology to tell a story when we go and present our findings. Reproducibility also makes it easier to defend decision-making. If we start producing the same answers over and over again, it's less about gut instinct and a lot more about data-driven insights. And finally, if we have reproducible workflows, other people can go in and audit our work to make sure that it's correct and that it complies with regulation. In my job, I deal a lot with healthcare data, and one of the things I need to do is make sure that patient data doesn't leak in any of our models. We have some spots at the front if you want to come up. So this is a high-level overview of the data science process. We start by asking an interesting question, like, what are we actually trying to do? And the next step, we'll start gathering data to answer that question. And this phase is probably going to involve us taking data from a format we're storing it in, and we'll transform it to a format we can actually use for our analysis. And then we'll do some data exploration. Next, we'll model the data. So this means building a model, fitting a model, and then tuning that model. And finally, we'll present our results through a presentation, a blog post, or a paper. So Python has a really great ecosystem of data science tools that make it really easy for us to do analysis. And Jupyter's sort of the star of the show. Jupyter's our data science front end, which we can use to capture our results and our process. So Jupyter notebooks are documents that contain live code, equations, visualizations, and explanatory text. So this is a picture I got from the Project Jupyter website. So you see we have some text, some formulas, some live code, interactive sliders, as well as some visual output. And we can use all of these components as building blocks when we're going to document our data science methodology. And then we can also pass these notebooks around when we want to share results with colleagues. But not so fast. Jupyter notebooks suffer from one problem, and that's the it works on my machine problem. In order for our notebooks to work, users are going to need to have access to our data, as well as the dependencies that were used to produce that original notebook. And this is where Docker's going to come in. Docker's going to help us solve that problem of it works on my machine. So Docker's a platform that allows us to package and run applications in loosely isolated environments that we call containers. We can use the shipping container analogy to understand how Docker works. Shipping containers, they standardized the logistics industry. It didn't really matter what was inside each of these containers. We can send them by boat, by train, or by truck. And we have the infrastructures at all these various facilities to handle these standardized containers. With Docker, we can package up our code, plus everything we need to run the code, into an isolated container. And since these software containers are standardized, we can ship them off into different environments without having to worry if they're going to run or not. So this does sound really similar to the concept of virtual machines, but there are a couple of key differences. The first is that Docker, it runs natively on the host machine. That is, it shares the same kernel as the host machine. And for virtual machines, we have a hypervisor. And this hypervisor provides each VM with virtual access to the host's resources. So what this really means is that for containers, we don't need full-scale operating systems, so they're going to be a lot more lightweight and have better performance characteristics. We can use Docker for many different things, such as streamlining our development workflows, if we ever want to do some continuous integration, some continuous deployment. We can use Docker to build out microservices, and of course, we can use Docker to do some reproducible data science. So this is a high-level overview of the Docker architecture. We have the Docker client, and that's where we enter in commands to interact with Docker. And these commands, they go to the Docker host. And this host can be running either on your local machine or a remote machine. It just needs to be running the Docker daemon. So this Docker daemon is going to be intercepting commands from our client. It's going to be managing Docker objects like containers, like images, and it's also going to communicate with other Docker daemons. And then we have the Docker registry, and that's where we store Docker images. Docker Hub, it's like GitHub. It's the public registry. So there you're going to find a lot of Docker images for things like Linux distributions, databases, and Python has a bunch of images up there as well. So here's just a screenshot I got from the Python Docker Hub page. You can see that we have all these tags, and this is what we're going to pass in when we're actually building our image. So what's an image? An image is a frozen snapshot of a container, and each image consists of a set of read-only layers that are stacked on top of each other. And each layer, it's the set of differences from the layer below it. Containers are the runtime instance. When you create a container, what you do is you add a thin read-write layer called a container layer to the top of the image layer stack. And then anytime you say you want to add a file, modify an existing file, or delete a file, all of those changes are going to be done in that top read-write layer, that top container layer. You can think of this really similar to the principles of object-oriented programming, where images, they're like classes, layers can be akin to inheritance, and containers, they're the runtime instance, just like objects are runtime instance of a class. So now we hit our first lab. So if you go to this bit.ly URL, and if you have not got a chance to get Docker and Docker Compose installed, we have some extra time in this lab to get that process going. So we'll be walking around the room. If you guys need any help, please let us know. We'll be happy to drop by. everyone, if you have a Windows machine and you want to get Windows machine? Yeah. good for everybody? Anybody need a hand? Don't be shy. It's in the repo. Here, I'll show you. What are we looking for?
The virtual, this in the virtual box. Like, what's the path to that?
Oh, yeah, it's right here. I have it in here. It's right here.
Okay.
Yeah, it's just home directory. Yes. All right, we'll start wrapping it up in 2 minutes for the next section. What's up? This is all on our this is all on the internet, so it's yeah. If you go to our repo, where are you going? There's a spot at the front if you want to come up. Start wrapping it up. Yeah. Yeah. All right, let's start wrapping. Yeah. Yeah, let's start wrapping it up, and we'll go on to the next section. Yeah. So now you played around with Docker a little bit, just got a little bit sense of the Docker client command line. Let's understand exactly like how Docker works. So we had a Docker image. How do we build these images? Well, there's two separate ways to do it. The first way to do it is we take our container, that runtime instance, and we'll freeze it using the Docker commit command. And what that's going to do, it's going to take that top read write layer we talked about, that top container layer, and it's going to make that read only. And now you can use this new stack of layers, a new image, to generate a new container. Or the more preferred way to do things is to use a Dockerfile, and a Docker build command. So the Dockerfile is a file that contains commands that are used to build an image, and we can automate our build process using Docker build. So this is a list of common Dockerfile commands. We have from, and that's going to allow us to set the base image, so we can use any of those images that we found on Docker Hub as a base image. We can also add metadata to our image. If we ever want to copy files and directories into our image, we can use the copy keyword, and we can set environment variables as well as the working directory. We can use the run keyword, and what that's going to do, it's going to execute shell commands, and it's going to put those new commands in a new layer at the top of the image layer stack. So just be aware that anytime you use any of these Dockerfile commands, we're going to be creating a new layer. So say you want to install Jupyter and pandas, you do a run pip install Jupyter. On the next line, you'll do a run pip install pandas. You're going to have an image with 2 layers. But Docker best practices says that one of the things we want to do is we want to reduce the number of layers inside of our images. So we can do this by chaining together commands exactly like we would at the command line. We can do a run pip install Jupyter, double ampersand to chain them together, backslash to go on the next line, pip install pandas, and that image is only going to have 1 layer inside. We can use entry point and CMD to define what our container should do at runtime. So what shell command should be executed every time our container launches? So there's 2 ways to put this in. There's the shell form, and that's pretty much what you would put in at the terminal. And then there's the exec form, which is the same thing, except it's formatted just a little differently. Be aware that entry point and CMD do interact really well. It's a little bit more of an advanced concept, so I recommend using CMD if you're just getting started. So let's go look at a hello world Docker file. And for this, we'll actually go into the terminal, and we'll create this file. So in this directory, I have two files. I have a hello world py file, and that's just going to be printing Python hello world. And then I have a Docker file. And let's take a look at this Docker file. So as I mentioned before, every time we use a Dockerfile command, we're going to be creating a new layer. This time, I'm going to be building off the Python 365 Alpine image. We're going to be setting our working directory, copying the contents of our current directory into that working directory, and then finally, when the container launches, we're going to run Python on our hello world script. We can use the docker build command to build images from these Docker files. So this time we'll tag it, we'll call it hello world. I'll also give it a tag, and also give it like a version. So that'll be :0.0.1, use semantic versioning always. And I'm going to say my Docker file is in the current directory, and that's the dot at the end. It's going to go out and build my image. So let's go take a look at our images. So we can do that using the docker images command. So you see here we have hello world. It has our tag, it has our ID, and it was built 2 seconds ago. We can now use this image to generate new containers. So doing that, we can use the docker run command, and then we'll put in our image name, and we call this hello world, and it had a version as well. The container is going to launch, and we're going to go in and run the Python process on our hello world script, and you see that it printed hello world. We can take a look at all of our running containers using the docker ps command. And so you're not going to see our hello world image here since this container stopped. The text is a little hard to see, but it's not there. But we can see all stop containers using the docker ps -a flag. And you see here we have our container ID with our image. It executes the command python hello world, and it has a name, angry Samit. So we can now take this container name and use it to restart the container. So we'll do a docker, it doesn't need to move this to the top, so we'll do a docker start, -i to make standard in active, -a to connect standard out and standard error. And then we'll put in our container name, and it restarts that process with the Python process, and it prints that hello world script that we said. We can also use the container ID, so docker ps -a, and this container ID is right here, just that hash you see. So we can do a docker start -i -a, and then the container ID, and it goes out and it prints that hello world to our terminal. So here are just the steps I walked through to build an image. And these are the steps to start a container and then restart a container. So you saw me use the docker run command, and that's the command you're going to use the most, since it's going to allow us to create containers from these images. So we should just explore it in a little bit more detail. We can use the -d flag to run it in detach mode, so run it in the background. I already mentioned how we can connect standard in, standard out, and standard error. We can also name our containers, and if we ever want to pass in parameters to our process, or maybe go to our shell, we can pass in bin/sh or bin bash to go to each of those respective prompts. So just be aware that anytime we delete a container, we're going to be deleting everything in that container. So all of that data in that top read-write layer, it's all going to go away. So we should be cognizant of how we can actually manage our data. So the simplest way to do things is to use the docker cp command, and we can use that to copy files in and out of our containers, but that's going to get a little bit tedious. So the more preferred way of doing things is to mount a data volume. So what this is going to be, it's going to be a local folder that you mount as a directory inside of your container. And then any changes you make in that directory inside of your container, it's going to be persisted on your local hard drive. And then when we're creating a container using the docker run command, we can use a -v flag to set the host path we wish to connect, as well as the container path we're going to be mounting to. In our Dockerfile, we can add a volume command to our Dockerfile, just to specify where our mount point should be, but be aware this doesn't really do anything. It's only really done to be explicit about where our mount point is going to be. We will still need to use the -v flag to make that connection. So containers can connect to the outside world fairly easily, but we'll need to set up port forwarding to connect to processes running inside of our container. This time when we're creating a container using the docker run command, we'll use the -p flag to specify the host port we wish to forward, as well as the container port we wish to expose. And this time we'll use we'll use an expose command in our Dockerfile just to be explicit about where we're actually going to be, what ports we're going to be exposing to the outside world. This doesn't really do anything. We'll still need to use the -p commands to specify those ports and what we're forwarding. So let's go through some Dockerfile best practices. I'll say this one more time. Be explicit about your build process. We're at a Python conference. Explicit is better than implicit. Containers should be stateless. If you're installing things, make sure you only install the things you need. You want your images to be as small as possible. To that point, make sure you're clearing up the cache if you're installing something. This is more for microservices, but if you have a container, it should only really have one concern or one purpose. We want to minimize the number of layers inside of our image. And the last one I'll mention is that in older Docker files, you'll see a maintainer command, but that's actually been deprecated, so try to use label if you can going forward. Let's walk through the Docker container lifecycle process one more time, just to make sure we understand all of these concepts. We have a Docker file, and then we'll use Docker build to build our image from that file. We can create a container using Docker run. We can also kill a running container using Docker kill container name. And what that's going to do, it's going to send a sigkill to the process running inside of that container. If we ever want to remove a stop container, we can do Docker rm container name. And if we want to delete our image, we can do Docker rmi image name. This is a list of Docker commands for containers. I put stars next to ones I use more than others. This is the same thing, except it's for images. Some more tips and tricks. Smaller images are better. Maybe it's time to explore some other Linux distributions like Alpine Linux. That's only 5 megabytes total. And the last one I'll mention, if you're ever running a process inside of your container, make sure you set its IP address to 0.0.0.0. If you use 127.0.0.1, that's going to be a loopback interface, and we're not going to be able to connect to that process. So this brings us to the second lab, and this is going to be a Dockerfile lab. And so here you're just going to create your own Dockerfile and then use that to build your own image. We'll be walking around the room, so if you have any questions from this lab or the previous lab, feel free to reach out. up in the next 2 minutes. So we'll start wrapping up this exercise. This is more just to get you familiar with like the Docker workflow, where you're just like creating your own Docker file, using that to build an image. We're gonna have more examples of this in a data science context, which fits in a little bit more with like the theme of our tutorial. So does anybody have any questions at the moment? We're all good? Awesome. So now let's learn how we can actually fit in Docker into some of our data science workflows. So imagine you have a Jupyter notebook you want to share. This could be a thesis, a project deliverable, or an analysis you want to send to a colleague. But Jupyter notebooks suffer from that problem we talked about earlier, the it works on my machine problem. So why don't we create a Docker image that contains our notebook, plus all the things that are required to produce those original calculations, and then we'll push that image up to Docker Hub. So this is my Docker file. I'm actually going to go into the terminal, and we'll take a look at this. So here I have three things. I have a Docker file, I have a data folder, and I have an iris analysis Jupyter notebook. Let's take a look at that Docker file. So this time I'm going to be building off the Python 365 Slim image. I'm setting some metadata, setting my working directory, copying the contents of our current directory into that working directory. I'm pip installing some required libraries, so this time I'm going to need NumPy, I'm going to need pandas, Seaborn, sklearn, and Jupyter. Make sure I clear the cache with this option. I'm going to make the port 8888 available to the outside world, and when the container launches, we're going to run Jupyter Notebook on our IP address, set the port, and since we're in a container, we don't need a browser to pop up. And also, we're going to be root inside of our container, so we just need to turn that option on just to make sure it runs. I'm sorry, but like, so yeah, if we can go, see. So the question was, why do we have a no cache option? And this is in order to keep our Docker images really small. Because if you have an image with their cache, people are just downloading your cache, but not actually going to be using it. So I'm going to actually take this image and use it to, so take this Docker file and use it to create an image. It's going to take some time, so I'm not actually going to go through the actual commands, but you can see I did do this a little earlier. So we have them right here. So I have my workflow number 1, and that's called a self-contained container. So let's actually use this image to generate a new container. So we'll do Docker run, and we'll connect the port. This time we want to make 9999 our port we want to forward on our local machine, and we'll expose the Jupyter running instance of 8888. We'll put in our image name, and we'll let it go. And so here we have a URL. So let's just take this token. And we'll go to localhost 9999 and paste in that token. So that token was right there. And there we go. We have this the same IPython Jupyter notebook and data folder that we had on our local machine, except this time it's inside of our container. So let's open this up and just to make sure everything works. So here I'm just going to be loading all the dependencies. Notice I have Python 3.6.1 on my local machine. Yes, I know I'm a dinosaur. And then when I refresh it, it goes Python 3.6.5, just like we specified in our Dockerfile. And now we can load in our data set, do some exploration with pandas, do some visualization with Seaborn and Matplotlib. And at the bottom, I'm using some sklearn to do some machine learning. So here I'm just going to be fitting SVM classifier. And there's an image down here, so let's just make sure that image comes back. And it comes back. So everything's working inside of the container, and we can pass this around. If we say have a thesis, we can bundle up all our files just so we know it's always going to run. We never have to set up any sort of dependencies. So now I'm just walking through the steps I use to build an image, initialize a container, and then restart a container. So now you have an image. Let's actually push it up to Docker Hub. So this process is really simple. You'll need to create an account on Docker Hub. We'll do a Docker login to log into our account. Do a Docker push full image name with our user ID, so it goes to the respective spot we expect. And then we'll have instructions for our users to Docker pull our image, and then they can initialize containers and then restart containers as they require. So those of us who work on teams understand how hard it is to standardize a development environment. Or if we've ever accidentally upgraded a dependency and had everything break, we know how important it is to keep all of our virtual environments isolated. So this is where workflow number 2 is going to come in. And I call this the data science project. So here what we're going to do is we're going to create a team or a project image using Docker, and then we'll mount a data volume that contains our notebooks as well as our data so we can have persistent data across all of our machines. So some of the benefits of this is that we can separate out our projects. If we want to onboard a new employee, they can just spin up a new container. And if we ever want to upgrade our dependencies for our project, say Pandas releases a new version, we can put that new version in a new container and put it through our automated testing pipeline. We're all testing, right? So let's go into this into this folder and take a look at this Docker file. So here I just have a Docker file. So let's take a look at that. So this time I'm going to be building off the mini conda image, and mini conda is just Python with the conda installer. Conda is really popular for data science, so I thought it'd be really fitting for this example. I'm setting my metadata. I'm setting my my working directory. I'm conda installing some of my required libraries, making sure I clean up the cache. And then I'm going to be exposing the port and creating a mount point. And just like before, I'm going to be running Jupyter Notebook when this container launches. So like a cooking show, I did do this a little earlier as well. And we have our workflow number 2 right here. So let's use this to build a new container. So we can do that using the docker run command, which we're familiar with now. We'll connect our port. Let's make it 9999 on my local machine again. And we'll forward the Jupyter running instance of 8888. And this time we're mounting a volume. And so I have a folder on my local machine where I store some of my data science work. So let's actually mount that just to make sure everything is working the way we expect. Oh, sorry, it's not this tab. And then I'm mounting it to /app. And this is why it's really good to be explicit, just in case you forget. And now we need the image name. I have that in a separate tab. And there it goes. Docker's going to create a new container and start the Jupyter process in that script. And then we have a URL. Let's actually take a look at that. And this was 9999 on my local machine. And you see here I have the same folder structure I have in my container that I had inside of my folder on my local machine. So the mounting is working exactly as we expected. Maybe a really good workflow for this would be having all your data and your notebooks stored on a network drive somewhere, so data is persisted across the entire team. This is just walking through the steps to build an image, initialize a container, and then restart a container. So with workflow number 3, which I call the data-driven image, or the data-driven application, I'm going to simplify the deployment process. Because normally when we've all manually deployed apps before, we run our tests in dev. If things pass, we move to prod, and then we're going to run our tests again in prod, just because we're not sure if everything's actually working. So why don't we use Docker to actually deploy our image? So we'll build our image, and we're going to know it's going to work across all these various environments. So for my image, what I'm going to do is I have data stored on my local machine, and I'm going to use Plotly's dash library to create a dashboard. And then anytime I want to view that dashboard, I can just spin up a container and go to a URL. So we'll go through this example as well. And so here you see I have a Dockerfile, I have a plot time series file. This is all on GitHub, so you can take a look at that at your convenience. And I have a requirements file. So we'll take a look at that really, really quickly. So here I'm just going to install some of the requirements I need to actually run this dashboard. And now let's take a look at our Docker file. This time I'm building off the Python 365 Alpine image. I mentioned Alpine's a really small Linux distribution. I really like using it for my my data-driven applications. I'm going to give some metadata, set my working directory, copy the contents of my current directory into that working directory, pip install that requirements file. I'm sure everybody's starting to see a pattern in these. Expose the port, and here I'll create a mount point at app/data. So the only difference in this one is I'm going to be using entry point just to define that Python is my default executable, and I'm going to be using CMD to pass in the parameter. So it's going to be plotting. It's going to be creating a dashboard for plot time series. If I had another script, I can pass that in at runtime to spin up a different container if I so choose. And so this one has also been pre-built, so we can just take a look at that really quickly. Right here, workflow number 3. So we're actually going to be using this to create a container. So we'll do that using Docker run. We'll connect our port. This time, let's use the standard port of 8050. And now we want to mount a volume. So just start one thing going. So since I got here, I've been generating data between 1 and 5 every 2 seconds. And that's in this file right here. So you can take a look at that. Yeah, it looks good. And now we can, let's get the PWD for this. And we'll get the working directory, and we'll mount that inside of our container. And it mounts to app/data. Again, this is why it's good to be explicit. And now it's running this process inside of our container. So let's go to this URL. So you can see our dashboard is updating exactly as we expect. So let's actually make sure it's working. I have another script on my machine that generates data every half a second. And let's start running that. And now you can see the points are a lot closer together. So it's working exactly as we expected. So a good workflow for this, instead of maybe having a file on your local machine, point it to a database somewhere and have your dashboard update whatever delay you want to set your event timer to. And this is going to be just walking through the steps I did to build an image, start a container, and then restart that container. This brings us to lab 3, and here we're going to be implementing 2 of the 3 workflows I showed you. We're going to be walking around the room, so if you have any questions, please let us know. And I think this should take us into the break. bring 20. And then, yeah, if you guys want to hang out, need some help, we'll be around. Yeah.
test. Here it is. Great. I'm going to get started on the next section. So Docker Compose is a complementary technology to Docker. It's written in Python, and it's maintained by the Docker project. But what is Docker Compose? Docker Compose allows you to spin up an entire network of Docker containers with a single command and a single configuration file. It's a simple YAML-based configuration that provides an easy-to-use interface for working with Docker. So it takes all of the complicated commands that you were running while running through the labs and turns them into a single configuration file that you can run with a single command. It basically turns this code here into something that looks like this. Personally, I would not want to use Docker without using Docker Compose. It's a great tool. So what specifically is Docker Compose good for? Docker Compose is great for spinning up a local development environment. Let's say you have your application, and their application depends on a database or a data science API or some other little microservice. This is the microservices that you create that you want networked together and talking to each other. So Docker Compose is great for configuring that in a very simple way. And then in the spirit of reproducible data science, you can take that configuration, pass it to someone else, and they can spin up the exact same configuration that you have, including databases and all, with a single command and very little configuration. Docker Compose is also great for running your integration tests. So instead of having to mock out a whole bunch of different services, you can actually run your tests against those services. If you want to run a test against the little API that you created, you can test that and use the API rather than having to mock it. Also, this is beyond the scope of this talk, but if you want to deploy your code, there's a tool called Docker Swarm, which Docker also supports, that you can use a very similar configuration to your Docker Compose file and deploy that to your production environment with very little changes. So here's a very simple Docker Compose diagram. I'm going to talk a little bit more about this in detail later, but I just want to kind of mention the main parts are the services that run, which are your containers. There's a network that connects them, and then there's volumes that store your persistent data that those services generate and use. So installing Docker Compose is very easy. If you have a Macintosh, you can install Docker for Mac, and Docker Compose comes pre-installed with that. Or if you have Windows and you use Docker for Windows, Docker Compose comes installed with that. If you have Linux, the install command is a slightly different command, but it's pretty easy to run and pretty straightforward. Or since Docker Compose is built in Python, you can also do pip install Docker Compose, and you'll get it through a Python package. There's also other ways to install Docker Compose, but this will cover about 90% of what you need to do of the use cases. So Docker Compose makes use of YAML. And I'm sure many of you are familiar with YAML, but I just want to mention it's a simple text-based configuration file format that lets you represent lists and dictionaries and singletons in a very readable way. So on the left, there's a YAML file, and on the right, here's like the Python equivalent of storing the same data, just for comparison. So Docker Compose's main configuration file is called docker-compose.yaml. This is the main configuration file, and it's just a text file. It's placed directly in the root of your project, usually where your Git repository lives. So there will usually be one Docker Compose file per project. Services are the core building blocks of Docker Compose. So services basically run your application. You can think of them as the running instance of your Docker containers. So if you have an app that you want to build, you would deploy it as a service, and that would have your code. But services can also be things like databases and whatever else you want to run. A service should have one purpose, and it should run one process. Services can be networked together, and they can share and store volume or data through volumes. So taking a look back at our diagram from before, these are the services in this diagram. I'll get a little bit more into it. If you take a look at a Docker Compose file, this is what a basic Docker Compose file might look like with some services assigned to it. So in this example, we have a web, an app, and a database service. You can name these whatever you like, but I recommend naming them something short, so it's easy to type, but also descriptive. So in this case, these services are pulling down different Docker images like Nginx or Postgres, or a custom image. So these are the base image that these services are going to be based off of. So here's a really simple Docker Compose file. It defines a single service, and it's based off a Python Docker image. And all the service is doing is running a simple Python web server. I'll show a little bit more of this in a minute, but I just wanted to show you this is how simple you can make Docker Compose. It can be pretty straightforward, or very few lines. So in addition to making it easy to run existing Docker images as services, Docker Compose helps you build your Docker files and run those as services. So as you've seen before, there's the Docker build command, which you can pass in a bunch of arguments to build a Docker file and tag the image, and pass in some build parameters and a build context. You can represent the same information in a Docker Compose file. So I know this looks like a lot of text, but the point is you only have to specify this once, and then you can rebuild your Docker image as much as you want, and you won't have to pass in all these arguments at the command line all the time. So in this example, we have a build keyword, which takes a build context. Optionally, you can specify a Docker file. It will find the default one if you don't. You can pass in some optional build arguments, and you can tag the image with the image keyword in this example. So let's go through a very simple use case. So can you see this okay? Let's see. Here we have a very simple Docker file on the top. This Docker file pulls from a Python-based image, a Python-based Docker image, and all it's doing is running a simple Python web server. Then if we take a look at this Docker Compose YAML file, it's defining one service, and it's executing the build command, which will build the Docker file located in the current directory. So I'm just going to show you just the basic user interface of how you would work with Docker Compose. So if you run Docker Compose up --build -d, this will build the Docker files associated with the file and download any Docker images. And then it will run all of the services as defined in the Docker Compose file. And it will also do this in the background. So there we go. Now if I do Docker Compose PS, we can see that one service is running, which is the one we've defined. I can stop this really easily just by doing Docker Compose stop. This will take a second. Almost there. And if I do a Docker Compose PS, you'll see that the process is in an exited state. Then if I do Docker Compose down, this will destroy the containers and all of the related resources. So if I do a Docker Compose PS, nothing will be present. So that's just a very simple use case of how you can interact with Docker Compose. So here's a very simple cheat sheet of very common commands that I use when I'm working with Docker Compose. This is all the commands that really will get you 90% of what you need to do with Docker Compose. I use these all the time and very rarely find myself using much more than this. So the Docker Compose build or up and build command, that's the one you saw me before, where it builds any Docker files and then it runs the application. You can run start and stop and restart operations for Docker Compose, which will, by default, it will restart all of the services, or you can restart a specific service by giving it service name. You can destroy the application by running Docker Compose down. You can run an ad hoc command inside of a service by using the Docker Compose run command, or you can enter into an existing container or an existing service by using the Docker Compose exec command, or you can view the logs that the services are producing via standard out and standard error with the Docker Compose log command. Ports allow us to expose the Docker hosts to the services running inside of the Docker network. Without exposing ports, nothing in the outside world would be able to communicate with your app. So here's the Docker run command that you've seen before, specifying the -p option to map port 8000 on your local machine to port 8001 inside the container. You can also, in Docker Compose, you can specify a ports keyword, which will do the exact same thing. In this example, again, we're going to map port 8000 to 8001 for the service, the app service. So it's really easy to designate a port. Let's go through a quick example with this. So here's a very similar Docker file that you saw before. We're pulling from Python 3.6. We're doing some setup here, and the big difference here is we're copying an index.html file into a directory inside of the container, and then we're running a simple Python web server. Then we're defining a service, and the only difference that we're doing now as compared to the last example is we're setting a port mapping. We're mapping port 8000 on the Docker host to 8000 on the service. So if I do Docker Compose up -- build, and then run it in the background, we can do a Docker Compose yes, and we can see that it's running. And the difference you'll note here is now that there's a port section on the far right, which shows that we're doing the port mapping properly. So now, if I go to a web browser, and it's hard to see, but if I type port or localhost 8000, I'll get a response back from the service that indicates that we are able to communicate to the service from the outside world. And just to prove that I'm not pulling any tricks, if I do a Docker Compose down, and then once it stops, now if I refresh the page, I get a connection refused. Commands allow us to specify what runs inside of services. And you've seen some examples of commands. Without setting a command in either your Docker Compose file, oh, thanks. Okay. Without setting a command in either your Docker Compose file or your Docker file, nothing will run. So here's two different examples of how commands might work. All you need to do is provide the command keyword argument, or command keyword, and then the shell script or the command that you want to execute. And just as there is for Docker, Docker Compose has two different formats for executing a command: the shell form, which is on the top, and the exec form on the bottom, in which you provide the command as a list. There's slight nuances in how they're executed. So within the Docker ecosystem, there are multiple ways to run commands. And as you've seen before, you can use the Docker run command to execute a command on the Docker CLI interface. Or in the Dockerfile, you can set a default command which will run with the CMD argument to the Dockerfile. And if you don't provide an argument to Docker run, the CMD command in the Dockerfile is what will run. Now in Docker Compose, if you provide a command keyword in your service, that's going to be the command that's executed instead of the one in the Dockerfile. That will override the Dockerfile. Or you can provide a command on the Docker Compose command line interface if you use the Docker Compose run command and provide a command to that. So there's that will override everything. So a key concept for configuring your Compose app is the environment keyword. It's the main way to pass configuration variables to your application. And it sets environment variables, Unix environment variables, within your containers. So as you've seen before, if you use the Docker run command, you can use the --env or the -e option to provide key value pairs that will be set as environment variables that will be set in your container. So if you go into your container and you do an export, you'll see those in there. Similarly with Docker Compose, setting environment variables can just be configured in this way. You set the environment keyword for each service, and you can pass in different environment variables. This is really powerful because this is how you can pass configuration or environment-specific information into your application and how you can configure it. In this example, I'm setting some database credentials for the DB service, and for the app, I'm setting in some debug credentials. These are arbitrary. You can set them to whatever you want, but the point is you can pass in data this way. Also, there's an env_file keyword, which you can use in your Docker Compose file. This lets you provide an external file or a separate file for providing key value pairs that get set as environment variables. This might be useful if you didn't want to litter your Docker Compose file with a bunch of arguments or with a bunch of environment variables. You can just add them as a separate file that you can include and split things up a little bit. So if we just take a look a little bit of an example here, say we have a simple Flask app, and on the top right, we have a Docker Compose file which sets some environment variables called Flask_app and debug and port, and then we're running Flask run via the command. Then if we take a look at the actual application that's running, the demo_app on the right side, the key part here to notice is that we can read in environment variables from the Docker image or from the Docker container with the os.getEnv function. That's a standard Python function. To read in an environment variable, set it to a variable inside the app, and then use that to change the behavior of the application. So networks are the killer feature of Docker Compose. They're what allows services to communicate with each other, and they basically create tiny little isolated networks on your machine. They're really pretty cool. So here's our example image, our example configuration real quick. The network obviously is this blue part right here, and this is what connects everything together. So if you're using Docker by itself, you might have to run a whole bunch of these commands. You'll have to create a network. In this case, we're calling it internal, and then you have to attach that network to each of your containers when you issue the Docker run command, and only then, after doing all of that, you can the containers will be able to communicate with each other. Docker Compose, this can all be explicitly declared in the Docker Compose configuration YAML file. All you need to do is specify a network at the bottom of the file and give it a name, and then you can attach that network to each of your services. Then all of your services will be able to see each other and communicate with each other. But what's even better is you don't even need to do that. By default, Docker Compose will create a default network for everything inside of your application. It's sometimes nice to be able to explicitly set a network. You can have a little bit more control over the situation. But if you leave it off, Docker Compose will automatically create a network for you and set up all of those commands that you don't need to do anymore. This is really powerful, and it comes right out of the box when you're using Docker Compose. So one really cool thing is that the service name will become the host name of that service, and it can be referred to by other services running. So for example, if I were to set an environment variable called dbHost and name it db, which is the name of the database service, inside of the container, my application can reference that environment variable and actually connect to that database service as though it were connecting to some host out on the internet. So just for a really simple example of this, we have a Docker Compose. If we execute the Docker Compose run command to enter into the app service, we can, once we're inside the app service, we can ping the database service, and it responds as though it's just pinging any other application, any other host. One interesting thing about Docker Compose is you can set dependencies between services using the depends on keyword, and this allows you to indicate to Docker Compose that the database will, or the application will depend on the database. So that will mean that the application service will start after the database service spins up. Now the one caveat for this is that the the database, if the database command that runs to spin up Postgres won't necessarily be finished. The depends on won't wait for that to finish before the dependency is satisfied. So that's something you might have to work around a little bit. So volumes let you share data between services and also between your host machine and a service. Volumes also let you store data and persist data that your application generates or consumes. So taking a look at our diagram right here, the volumes would be the red portion. And in this case, the app and the web service are using a shared volume mount called static. And the database container is using a data volume that's mounting it to varlib Postgres data. So this goes back to, if you look at raw Docker, you have to create a volume, you can use the Docker volume create command, and then every time you have to run that volume, and every time you want to run your container, you have to attach that volume. Seems to be cutting in and out. Every time you run that container, you have to attach that volume to your service. So it's kind of a big hassle. But with Docker Compose, you can also specify volumes in the compose file by defining a volume at the bottom. In this case, we're calling it MyData. And then we can mount that MyData to a specific directory inside of the app and the database container service. Also, we can use a bind mount, like the second example, where we're mounting the current directory to a directory called source. That lets you bring your code into your application. So let's talk a little bit about advanced Docker Compose file usage. So by default, when Docker executes, it looks for a command inside of the current directory, or looks for a file inside of the current directory called docker-compose.yaml. And that's the one we've been talking about right now. But if you create a file called docker-compose override.yaml, Docker Compose will override any values found in there. It will merge that file on top of your Docker Compose file and override the base configuration. This is useful if you have multiple people working on the same project. You can all have your environment-specific tweaks that you can set in your own personal override files. Like if you want to set specific passwords or keys that are only relevant to you, you can do that in the override file, and it will override the base configuration. So, for example, if you, here's just, let's say you have a docker-compose.yaml and a Docker Compose override file. In this example, we're taking the image and we're overriding the image with experiments.001, and we're setting some ports, some additional ports, and we're overriding the environment variable called database_URL. So this is just a visual representation of what's happening. You can also pass the -f option to Docker Compose to specify different Docker Compose files. And you can provide multiple Docker Compose files that will override each other. They will override each other. And this gives you a lot of flexibility for defining different environments. So there are a few different rules that take effect when you're merging together Docker Compose files. For example, for single value items like image and command and entry point, the override file will completely replace the corresponding value in the Docker Compose file. For multi-value options like ports and expose and DNS, the override file will concatenate the values together from both files. And for key value options like environment or labels or volumes, Docker Compose, the override file will concatenate with the base file, but also replace the existing, any existing keys. So there's a few miscellaneous things that are worth mentioning about Docker Compose. One, when you spin up a Docker Compose application, all of the resources that are generated are prefixed with the name of the directory that you're currently in. So the containers and the volumes and the networks will have a prefix of your current directory. This helps prevent your containers, the name of your containers from colliding with other Docker Compose applications that you might have running on the same machine. So this is a way you can have multiple apps or multiple Docker Compose applications. Like if you have a Docker Compose service called app, you might have that defined in multiple compose files across your desktop, and this will prevent that from colliding. You can also pass in the -p option to the Docker Compose command line, and you can specify an alternate prefix, and this gives you some customizability about what that naming will be. And also, if you want to run multiple copies of the same Docker Compose app project, this will help you do that. So here's just a quick visual look at some of the naming of some of the resources. As you can see, the containers, volumes, and networks are prefixed with the Docker for data prefix, which just happens to be the name of the directory that I was in when I created these resources. So debugging is something you'll probably inevitably be doing when you're building Python apps and inside of a Docker Compose network. There's a few things you have to be concerned about. One is Docker Compose doesn't automatically pass in standard input. So in order to, which is kind of essential for a debugger, you need to be able to type things to be able to debug. So in order to enable that, you can set the std_in_open and tty flags inside of your Docker Compose file under each service. And this will allow standard input to make it into the container. In addition, if you're using like a process runner like Uwhiskey or Unicorn, there's some additional flags you'll have to pass in to make sure that those services are properly passing in standard input to the Python application that you're using. This is more of an advanced topic, but just be aware that if you need to do that, maybe refer back to the slide. Also, when you're developing a Python application, your application isn't automatically going to reload when you make changes to it. So if you're using, sometimes it can be kind of a hassle to completely stop your Docker Compose application and then restart it every time you make a code change. So for that reason, I recommend looking into auto reloading for your application. So if you're using something like Django with run server, Django will automatically reload your code whenever you make a change to the Python files. Or if you're using Uwhiskey or Unicorn, you can set some flags that will automatically reload your application upon making any change to it. These aren't something you'd want to set in production, but they're great for developing locally. So with any application, especially a data science application, data is key. And if you want to spin up a simple database inside of your Docker Compose network, here's a quick recipe how you can get a Postgres database up and running and available so you can use. This is just a very simple compose configuration. It's using the Postgres base image on Docker Hub, and it's setting some credential environment variables. It's setting up a volume mount so it will persist the data. And optionally, you can map a port to your local machine so you can access it locally. And getting data in and out of your Docker Compose network is pretty straightforward, even though it's a little bit more complicated than doing it normally. Here's a recipe that you can use to use a SQL dump or a PSQL command to get data in and out of your Docker Compose application. You can refer back to the slide if you want to use it. This I found really helpful because this is something I do all the time is make SQL exports and imports. MySQL is very similar. Here's a really simple Docker Compose config. Looks almost the same as the Postgres setting. And the import-export for that is very similar, just with the MySQL nuances. And this I purposely left small. It's if you want to import data into MongoDB, there's a lot more steps you have to do, but it's not too bad. If this satisfies, or if this is a use case that you're interested in, I recommend taking a look at the slide and the attached link. But this is one way you can import data into a MongoDB database. Also, if there's other services, they all kind of operate on the same principle if you want to import and export data through Docker Compose. So it shouldn't be too hard to use the same principles to do that. So in summary, we've talked about why Docker Compose is useful. We've gone over some basic command usage we've talked a little bit about the basic command line format, a little bit about services, networks, volumes, and environment variables, and talked about some useful, helpful hints. If you're interested in learning more, the docs are a really great resource for this. Also, I wrote a blog post about how to integrate Docker Compose with a Django project from scratch, and it might be a good resource to see a fully working example. And finally, this is a little off topic, but there's a great project called Compose with a K that lets you use a Docker Compose configuration to generate a Kubernetes deployment, which is something you might want to consider if you want to deploy a Compose network to production. Just that's an advanced topic, but something to look at in a pretty cool project. I hope you learned a lot about Docker Compose, and we'll move on to our next segment.
Hello? Okay, cool. So now you have seen Docker, and you have seen Docker. You have played around with the Docker in command line. Now, we will put this in context of a real-world application. So let's say you're a data scientist, and you have a cool app idea that uses machine learning. You have built a model in your Jupyter notebook, and it does great recommendations, but it's still in the Jupyter notebook. It's not in the hands of the users. So what we will see now is the steps that are required to Dockerize the model that you have built and expose it as a microservice. In the next section, we will see how Docker Compose integrates that microservice with other services in order to serve a fully fledged web app that the users can use. So by the next two sections, you'll have the steps that are required for taking a model and then building a full-fledged web app from there. So what's our cool app idea? We are very excited to be here at PyCon. There are so many great talks that you can go to. But wait, there are too many great talks that you can go to. Wouldn't it be nice if there was an app that told you which talks you should go to this year based on the talks that you went to last year and maybe years before that? Introducing Talk Recommender. Talk Recommender is like Tinder, but for PyCon talks. It takes the talks that you went to last year, and then it recommends which talks you should go to this year. Imagine the amount of time it will save for you. Imagine the time it will save for the 6,000 people who are coming to PyCon this year. This will leave us more time for hallway track and make great people have great conversations. So let's take a look at Talk Recommender in action. So this is how the interface looks like. As you can see, Talk Recommender is showing the user a talk from previous PyCon. This is from 2017 PyCon. The user can say that, yes, I will watch this in person, or they can say, I'll watch it later. Now, the user will go and say, give me some recommendations. So now, based on the input that the user provided, Talk Recommender has filtered out 94 talks. But the user can go back and say, I want a few less talks that I want to go to, and let's do a few more. Fuzzy search algorithm looks data sciencey. Let's do there. Snakes in the browser, maybe I won't watch it. Snakes on hyperplane machine learning, let's do this. And let's try the recommendations. Okay, so much better. Now we have 53 talks, leaving us more time for hallway track. So with that said, we will switch to the Jupyter notebook exercise that we have in exercise 4. What you'll find there, if you open it, where, in here? Okay. So exercise 4, you'll see data science essentials. Here, we are building a simple text classifier. And what you'll see here, we are loading the data, we are extracting features from it, splitting into training and testing set, training the model, and doing predictions from it. So it's a fairly simple text processing pipeline. We won't get into the details of the text processing, but we have provided references that you can follow up in your own time. So we were using just pandas and scikit-learn here. What you will do is you'll go to each of the cells, fill in the blanks wherever required, and run the cell by hitting Shift-Enter. Then when you come to the exercise number F, here, you'll take the code that you have written in the cells above and put them together in a model.py file that you will find in this directory. Then with one Docker command, which is provided here, you'll be able to serve it as a Flask microservice. Okay, let's get back into our exercise. Okay, we'll start to wrap up in a while. So did we get to a Flask service running in our container? Where are people now? What are we doing? Sorry? Still building? Oh my God.
We apologize for the Wi-Fi.
Yeah. So we will move on. The exercises that you have here, most of the code is written out for you. It's just a few fill in the blanks. The only place that you might spend some time looking at is this last part, where you have the data frame for 2018, and you have to index it using the predicted talk index. So you can use df 2018.loc and use predicted talk index as indexes there and filter out the columns that the question asks for. From there on, it would just be a copy paste from the cells into model.py, and you can run this command, which will serve the Flask app, and you'll get the predictions as a web service. So now that we have seen how to build a web service from a predictive analytics model, let's take a look at other parts of Talk Recommender. So if you go to the Talk Voter repository that we have in, along with the data science repository, you'll see the structure of the code is something like this. First, let's begin with the predict API folder. So in the predict API folder, you'll find the same model.py and app.py. These are the files that you have used in exercise 4. Along with that, we have resources.py and wizgy.py, which is required to run the Flask app as a microservice in the MuWizgy application server, which is a popular application server that we use. So one additional point here is, since we are now building a web app, we need a database instead of the CSV that we were using when we were using the Jupyter notebook. We need to store the input from the users into the database. Talk Recommender uses Postgres as a Dockerized service, and we will see that later. Next, we go to the front-end folder. As the name suggests, we have the JavaScript code in here, which serves our front end. Talk Recommender uses React, which is a popular JavaScript framework, to build out the components in the front end. And this is built as a single-page application, which talks to the REST API in the back end. The REST API is built inside the Talk Voter directory. It serves three main purposes. One is it handles the requests from the front end. Two, it stores the data into the database. And three, it connects to the predict API service and serves the recommendations that it generates when the user clicks on the recommend button. So here's how the different components of Talk Recommender interact with each other. So when the user clicks on an in-person or watch later button, the request comes to the app, and that is stored in the database. When the user clicks on the recommendations button, the request comes to the app goes to the database, fetches all the talks that the user has labeled till that point, and then it pushes that to the predict service. The predict service builds a model and then forwards the recommendations to the front end. So this is how all of these come together using Docker Compose. With this slide up, We will now transition into the Docker Compose lab, which is our last lab, where we will see how Docker Compose is used, and we will be making this application work with Docker Compose. So this is the URL for Docker Compose exercise.
let's start wrapping it up. Okay, so like we've been working with containers, we've been working with all these various workflows. What are some best practices for our workflows? So a lot of the things that we did was we installed images from, we used images from Docker Hub as our base image. And so that's probably the best workflow to do, because you actually know that these official images are the ones that these companies recommend. I already talked a little bit about versioning images. Just don't use the latest version. I would recommend using something like semantic versioning. This is something you should talk through with your team on trying to figure out like what we should do as an organization. When you're using containers, think of them as immutable objects. If you want to propagate a change to a container, don't go into the container and make that change. What you really want to do is you want to change the image and use that image to generate a new container, which we'll use to replace the old container. Very briefly, there's a thing called a multi-stage build. This is more for compiled languages. So say you have a build step, like where you're taking, like a JavaScript step, where you're taking all your node modules and you're generating like a .js like artifact. So instead of having all of that done in one container, let's actually use an intermediate container to actually build our image and then take that build artifact and then use that build artifact in our final image. And the last thing I'll mention is I've been running a lot of things as root in my examples. That's not really the best workflow, so try to use a non-privileged user. And I have added a link for further reading. And before we had the excuse, it works on my machine. Now we have the excuse, it works on my container. But seriously though, like if something's not working, like it's our problem and we have to fix it. I know we've had some issues today, but yeah, like definitely like we should figure out what's going on. We're here together as a team and we should be able to go down that route. So where can you guys go from here? I highly recommend checking out the Docker documentation, how to install Docker. Their Getting Started guide is fantastic. If you have access to a Pluralsight account, Nigel Poulton has a course called Docker Deep Dive. And surprisingly, CenturyLink has a really good Docker resource. And the last one I'll mention is Kubernetes. That's how you're going to deploy a lot of these containers. So there's a lot of information there. So I would just suggest maybe checking out Kelsey Hightower's information there. So that's pretty much it for us. We have links to our slides and our GitHub. If anybody has questions right now, we will definitely take them. Yes? Yeah. So the comment was about Windows having different line endings, and that might cause issues when you're loading some things inside of, loading Linux things inside of Windows. Yes? Yeah, for packaging up pre-trained models was the question. I have a workflow in the main Git repository for the tutorial. In data science workflows, it's workflow number 4. I call it the Data Science API. And so that actually walks you through how to build a Flask API step-by-step basis. Yes? So the question was about using Minikube versus Docker Compose.
Sure. So Docker Compose is really great for spinning up like a small to medium-sized application. It really hits the spot when you're, I've used it a lot for like running Django apps with a lot of service dependencies. So that's where I think the sweet spot with Docker Compose is. If you plan on deploying stuff to Kubernetes, then Minikube probably would be the route to go. It's, it's their recommendation for. So that's a good dev environment for running Kubernetes services. So that's how I kind of draw my. But Kubernetes is pretty heavyweight for a lot of applications, and so if you go down that route, you're going to have to also learn a lot of other stuff as well.
Anybody else? All right, thank you so much for coming out. Hope you guys learned a lot and had some fun with Docker.